All right, y'all. Let's go ahead and jump into notes. Hopefully, um, you participated in the do now because that was a warm up for today. In your notebooks, you need to write 1.4 notes. Continuity. Today we're talking about continuity. We'll be discussing what does it mean for a function to be continuous, and we'll also learn how to force continuity on a function. Okay, so this was your do now. I already posted a key, but uh, write your own definition of what it means for a function to be continuous. Um, I'm sure we got a variety of answers, but I just want to kind of like share what one of my teachers told me at one point that was really helpful. For a function to be continuous, you have to be able to draw on that function without picking up your pen. So, as you can see on number 4 here, I just drew on it without picking up my pen. Now let's check, can I do that on number 5? So I would say yes, that is continuous. What about for number 5? I'm drawing on the function, but here I have a hole. I am not allowed to keep my pen down on this hole. So I have to pick up my pen to keep drawing. So this is not continuous, no. What about number 6? Drawing. Oh no, if I want to hop over here, I have to pick up my pen because I cannot touch that asymptote. And then I can draw back onto the function. So that is not continuous because I had to pick up my pen. So continuous functions, number 8 is a yes. Think of it as you can draw on the function without having to pick up your pen. No, that is not continuous. Okay, now let's actually do like a formal definition. A function is continuous at a point, and you should write this down. Anytime we do like definitions, you should definitely write it down. So continuity, definition, a function is continuous at a point x equals c. So this is our x value in our point, x comma y. The x value would be c if, comma y, sorry, if, okay, we have 3 things that have to be true. 1, f of c exists. So what that means is there's a real value y value, here, let me write y value, at x equals c. There is a real y value at x equals c. Number 2, the limit as x approaches c of f of x exists. So the limit has to exist. And let's remember what that means for a limit to exist. Both, you need to write this down. It's a important thing to remember. Both the limit as x approaches c from the left have to exist, the left and the right, and they have to equal each other. So that's what we're writing down. The limit from the left as x approaches c must equal, you must get the same value as the limit from the right. All right, and then last but not least, we have the f of c, the thing from number 1. So like from number 1 right here, f of c, the number that you get, has to equal the limit as x approaches c of f of x. This is from number 2. The thing from number 2. So the numbers that you get here and here have to be equal to each other. That is the definition of continuity. Okay, so now let's actually learn about different types of discontinuities. So hopefully you got all of those rules down. These are extremely important for calculus. You will need to know all 3 of them, like have them memorized, and be able to use them in a proof. And that's what we're going to do today. All right. Types of discontinuities. So we need to know names of these because on the AP exam, they will tell you like there's a certain type of discontinuity and they'll say the name. Okay, so this one, first, we have a jump. This is called a jump discontinuity. Sometimes people call it a step jump or step discontinuity. I'll be calling it jump mostly. And here's the jump. That's the jump, right? your function jumps to another level. Okay, these holes, so make sure you note that these are holes. You should be drawing these graphs very, very quickly, like examples of these in your notes. So these are holes, but the technical term for them, they're called removable discontinuities. Removable discontinuity is a hole. That's the same thing as a hole. AP exam likes to call it a removable discontinuity. They're fancy. Okay, and then this thing, make sure you label that. That's an asymptote, that dotted line. If you have an asymptote, you have an infinite discontinuity. This is an infinite discontinuity. Okay, so we should have all three of those graphs down, and then the technical terms are at the bottom. These are what AP exam will use. Okay, 3 types of discontinuities. Let's move on. Now we're going to do a check for continuity. So please get this example problem down as fast as you possibly can. Get this example problem down ASAP. So examples, where is the function f of x, and this is a piecewise function, right, 2 pieces, f of x equals x squared for x is less than 0, and then f of x equals x plus 1 for x is greater than or equal to 0. Where is this function continuous? Okay, so we have 2 options. Option 1, look at a graph. That's the easiest way to tell if a function's continuous, right? That's what we did in the do now. But let's pretend that we don't have that option. So option 2, imagine the shapes. Imagine the shapes of the graphs. Of each piece. Write this down. So, remember in the AP summer homework, I said there's a bunch of shapes of graphs and you need to know the shapes. This is where that comes in handy. So, we're going to imagine the shapes of these graphs. We have this piece, x squared. Actually, let me do this in 2 different colors. So, we have x squared that I'm going to do in blue. And then in red, I'm going to do x plus 1. I'm going to sketch this really quick. We should know the shapes of both of these. So, x squared is a parabola. X squared is a parabola that has its vertex at 0. And then x plus 1 is a line that has its y-intercept at 1. Okay, so these are the shapes of the graphs. But then we have to think about the fact that these pieces only work for certain x values. So there's I like to call this point the problem child, the problem point. So this point right here, x equals 0, that's our problem child. So at x equals 0, which is right here, something happens. Something weird happens. So let's look at what happens. X squared only happens for x is less than 0. Remember, I think of these as arrowheads. So that's this way. The x squared graph, it's only the left side of the graph. So I'm going to erase my right side. And then is there an equal sign under this x less than 0? No, there's not. So we actually have an open dot right here. Oh, I knew that was going to erase my axis. What a pain. Okay, hold on. Let me put my axis back. There we go. We have an open dot at x equals 0. Open circle. Cool. And then for the x plus 1 graph, our arrow is pointing to the right. So that's talking about the right side of the graph. We actually don't need that function on the left side of the graph. And then we do have an equal sign here, so that's why that is a closed circle. Okay, cool. So now we can answer this question. Where is this function continuous? Where is this function continuous? Well, I would say everywhere except and then x equals, I want you to tell me, where is this function continuous? It's continuous everywhere except what x value? What x value is it not continuous at? Also, I want you to tell me what type of discontinuity it has at that x value. Go. Okay, it is continuous everywhere except x equals 0. Right here. There is a, you should have said jump discontinuity. Okay, at x equals 0. Let's move on. Cool. Now, where is this function continuous? I want you to do the same thing. Imagine what the pieces of this graph looks like. Now, before we draw the graph, we're going to get even more on our heads. We're not going to put the graph on paper. We're literally just going to think about each piece. So, what type of function is this top piece? What type of function is it? What's the name of that function? This would be a line. This looks like y equals mx plus b, right? So that's a linear function. What would we call this bottom piece? That's a cubic. Okay. Are straight lines continuous? Linear functions, are they continuous? Yes, they're continuous. These things are continuous, so that's good news. Are cubic functions continuous? Well, if you're not sure what a cubic looks like, really quick, a cubic looks like this, and it goes on forever. No holes, no asymptotes. So yes, cubics are continuous. Okay, so what's our problem child? What's the potential point that's going to cause an issue? X equals -1. That's going to cause an issue. So what we're going to do is we're going to go through the test for continuity. Let's go back up to where we talked about that. First of all, f of c has to exist. Then the limits from the left and from the right have to exist. So let's go through that test to check if this is continuous. And again, you should have this example down. Anytime I have an example, make sure you get it on your paper. So first thing we're going to do for the continuity test, does f of c exist? Well, c is going to be your problem child. So what is the x value that's a problem child? -1. So f of -1 equals, okay, we need to look at the piece that you are allowed to plug, oh gosh, I don't know why that happened. Sorry, y'all. So we're going to look at the piece that allows you to plug in -1. So let's go over here. Which one says equals -1? The bottom piece. So we're going to plug -1 into this piece. We get -1 cubed plus 5. That equals 4. Because -1 cubed is -1. Okay, cool. Does f of c exist? Yes. Yay. Okay, f of c exists. Now we need to do the second step. Step 2. What about the limit as x approaches c, or in this case, -1 of f of x? Does that exist? Well, as you know, we need to check both the left and the right limit. So let's go ahead and do that very quickly. We're going to do the limit as x approaches c from the left. Oops. Instead of c, let me write -1 because we know that's the problem child. Oops. From the left of f of x. And that is limit as x approaches -1 of the left piece, that's this arrow pointing left, is 5x plus 3. Since that is a continuous straight line, we're allowed to substitute, so we have 5, -1 plus 3 equals -5 plus 3, -2. Okay, cool. Now let's check the limit from the right, or of the right piece. Okay, so limit as x approaches -1 from the right of f of x equals the limit as x approaches -1 of the right-hand piece, that's this arrow, that arrow is pointing to the right, so we're going to plug in x cubed plus 5 for the right-hand piece. And because this is a continuous function, we are allowed to substitute, so we get -1 cubed plus 5. Didn't we already do that? -1 cubed plus 5? Yeah. So we know that's 4. Okay, cool. Why are we doing this again? Why are we doing this? We're trying to check, does the general limit exist? Does the general limit as x approaches -1 of f exist? For that general limit to exist, these numbers have to be the same. So no, the general limit does not exist. So here's what we're going to say. We're going to say the limit as x approaches -1 of f of x dne does not exist. And then we would conclude, so f of x is not continuous. At what x value? What was the problem, child? At x equals -1. Sad, we're not continuous. Oh no. Okay, good news. We're going to learn how to make this function continuous pretty soon. Okay, but before we do that, I want you to try this problem on your own. Try this problem very quickly. Where is the function g of x continuous? Oh, shoot. Hold on really quick, y'all. We will say, if we're answering where is the function continuous, we would say f of x is not continuous at x equals -1, so f of x is continuous. It was asking where is it continuous? Everywhere. Oops. Everywhere. Except x equals -1. We have to make sure we answer the question. That's always tricky about AP. They ask, where is it continuous? Not where is it not continuous. So, where is it continuous? F of x is continuous everywhere except x equals -1. Okay, cool. Let's move on. Y'all are going to do this one very quickly. Tell me, where is the function g of x continuous? Go. All right. We're going to go through all the steps. So first, does g of the problem child, does g of 3 exist? Well, this is where 3 is allowed to be equal, or x is allowed to be equal to 3. So we're going to use this piece to plug in 3. So we get 3 to the 4th minus 74. Okay, do I care what that number is? No, that's a number. So does g of 3 exist? Yes, g of 3 exists. Now, eventually I will have to care what that number is, but I was just trying to show y'all that it is possible to save time by not stressing about whether or not the number exists. Okay, and just so you know, you get 7. So if you followed that all the way through, you should have gotten 7. Okay, 2. We need to check, does the limit as x approaches the problem child, which is 3, of g of x exist? Does that exist? Well, let's take the left and the right limit. So over here, I'm going to do limit as x approaches 3 from the left of g of x. That's equal to the limit as x approaches 3 of the left piece. This guy is pointing left, so that's this piece. 3x minus 2. That's continuous, so I'm allowed to substitute. We get 3 minus 2 equals 3 times 3, 9, minus 2, 7. Oh, this is looking good, y'all. We have 7, 7. Let's keep going. Okay, now we need to check the limit as x approaches 3 from the right of g of x to make sure that this general limit exists. That's the limit as x approaches 3 of the right piece. This arrow is pointing right. So we're going to use that piece. Well, didn't we already do that? Didn't we already plug 3 into x to the 4th minus 74? Yes, we did. So we can say we already did this, and we know that it's 7. See how I was saying eventually you're going to have to solve this number? Okay, the reason we have to solve is because we have to check, are these equal? Does 7 equal 7? Yes. So the limit from the left is equal to the limit from the right, so you could say the general limit exists. This general limit equals 7. All right, step 3, we did not make it to step 3 last time because the general limit didn't exist. But let's go to step 3. Step 3, we have to check, does f of c, the number you got from the first thing, equal the limit? Does g of 3, so step 3, does g of 3 equal the limit as x approaches 3 of g of x? That's a question. Yes, it does, because g of 3 was 7. So 7 equals 7. Yay! It asked, where is the function continuous? The answer is everywhere. G of x, I'll answer it red just like last time, sorry. G of x is continuous everywhere. And then we'll say even at x equals 3. That was our problem child. Okay, cool. So now that you know what continuity looks like algebraically, we are going to force functions to be continuous. So write this down. Force two functions to be continuous at a point. And y'all are doing great. We're almost done with notes. Okay, find the value of b that makes h of x continuous. Here is h of x. So what we're going to do is we're going to work through the steps of continuity. So first, problem child is 2, right? So we're going to check, does h of 2 exist? X is allowed to equal 2 for the top piece, so we're going to plug 2 into the top piece. And when you simplify that, you should get 4 minus 10, that's negative 6 plus 3, negative 3. Cool. 2, we have the limit as x approaches 2 of h of x needs to exist. So let's go ahead and do left and right limits. I'm going to do those over here. The limit as x approaches 2 from the left of h of x equals the limit as x approaches 2. My left piece is the top thing, x squared minus 5x plus 3. We already plugged that in, so we know that's negative 3. Let's do the limit as x approaches 2 from the right. Limit as x approaches 2 of the right piece, thing pointing right. That is bx plus 1. Okay, cool. Here's the thing, y'all. Don't plug into the wrong thing. What does it say right here? X. So what letter am I allowed to plug the 2 into? X. Okay, leave the b as b. It's a b. It's okay. So we have b2 plus 1, and this would be 2b plus 1. True? All right. So, really quick, what needs to be true for the general limit to exist? For this general limit to exist, we need to have the left limit, which is negative 3, equal the right limit, which is 2b plus 1. So what are we going to do? Set the left limit equal to the right limit. Okay, so here we go. We're going to say let negative 3 equal 2b plus 1. Then when we solve for b, when we find b, we're finding the b that makes h of x continuous. That's what the problem asks us to do. So let's solve for b very quickly using algebra. Solve for b using algebra. We have minus 1, that's negative 4 equals 2b. Divide by 2, divide by 2. We get negative 2 equals b. Okay, so we found the b that would make the limit exist. What this means is, that would make the limit be negative 3 for the right side. What this means is, if you put a 2 here in b, if you put a 2 in the place of b, this function is continuous all the time. Always. That's what we did. We force it to be continuous all the time. Sweet. Now it's your turn. So I want you to try this one. It looks scary. I promise it's not, though. You try to find the value of a. Find the value of a that makes g of x continuous. Go. Okay. So let's go ahead and very quickly go through these steps. 1, g of negative 2 equals, I'm going to plug into this function. 9 minus negative 2 squared equals, that's 9 minus 4, which is 9 minus 4, 5. Okay, so we have g of negative 2. Now we need to do the second step. Limit as x approaches negative 2 is c here, of g of x. So I'm going to go over here and do the left limit. That would be the left function, which is a over x squared. Again, I can plug in negative 2 into x, so we get a over negative 2 squared equals a over 4. All right, we're stuck. We're done there. Let's keep going. We need to now find the right limit. Equals limit as x approaches negative 2 of the right piece, which is that 9 minus x squared, equals, we already found that, it's 5. Okay, we need the left limit. The left limit, which is this thing, needs to equal the right limit, which is this number. So let's go ahead and set those equal. So we have a over 4 equals 5. Solve for a. We're going to do times 4 times 4. A equals 20. All right, that is the value of a. That will make this last step true. If a equals 20, then 3 happens. We get g of negative 2 equals the limit as x approaches negative 2 of g of x, which equals 5. Sweet, we're done. Let's practice.